Hi, I am Sanjay Patel. In this lecture, we are going to understand how to transform a double integral from Cartesian coordinates into polar coordinates. We know the transformation formula uh, for transforming double integral f of x comma y dx dy over a given region R into polar coordinates. And the formula is given by this. We replace x and y by x is equal to r cos theta and y is equal to r sin theta. This is the relationship between the Cartesian and the polar coordinates. So we substitute everywhere x and y as r cos theta and r sin theta. And this becomes this function small f of x comma y becomes function of r and theta, and this dx dy is replaced by mod j Jacobian into dr d theta. But the Jacobian we already obtained, so it can be written as r into dr d theta. So let us take problems based on this transformation formula from Cartesian to polar coordinates. Polar coordinates in R2. Okay, so let me explain all this by some examples. So first example I am taking here is this one. Say evaluate the double integral of the function x square plus y square raised to minus 1 by 2 dx dy, where the limits of integration is x equal to 0 to 1 and y is equal to say x square to x. Okay, by changing it into polar coordinates. Or even if it is not given that by changing into polar coordinates, whenever a function contains this kind of expression x square plus y square or square root of x square plus y square or some power of x square plus y square, it is sometimes easy to transform into polar coordinates, because we know the relation between the Cartesian and polar is x square plus y square is equal to r square. So we can use that relationship to simplify this problem. One more thing I want to tell you here is in this problem I have written the lower limit as x square and the upper limit is x. It is not a mistake. Generally, lower limit is always less than the upper limit, but in case of a number lies between 0 and 1, here 0 is less than x is less than 1. So if you multiply it by x, so you get 0 less than x square less than say x. So x square is always less than x, and therefore it justifies this thing. In 0 to 1, this x square value is always less than x. Okay, so here the limits of integration, or the region of integration, you can say, region of integration is bounded by the four curves x equal to 0, x is equal to 1, y is equal to x square, and y is equal to x. Okay, now first of all let us find the point of intersection of these curves and these constants, or these four curves. Let us say like this. Here for y is equal to say x square, when you put x equal to 0, we get y is equal to 0, and when you put x equal to 1, we will get y is equal to 1. So the point of intersection of the two lines x equal to 0 and x equal to 1 with this parabola y equal to x square are 0 0 and 1 1. The same way for y equal to x, again if I put x equal to 0, y is equal to 0, When x equal to 0, we have y is equal to 0, and when x equal to 1, y is also equal to 1. So again, this curve also intersects the two lines in the same points. This is a parabola and this is a straight line. So let us draw the region of integration to understand this. So I will take the x-axis, y-axis, say this is our x-axis, okay, and y-axis. And let us take a straight line y is equal to x, which is passing through the origin. That straight line is, say, this thing passing through origin and making an angle of 45 degree. So it is this line. Let me okay. And the parabola, this is y is equal to x line, and the parabola is given by, let me write, parabola is something like this. It's not proper. So this is my parabola. Say, let me okay. So this is y is equal to x square. This is not drawn properly. It is y is equal to x square. This is the parabola. And our region of integration is the region lying between this y equal to x and y is equal to x square. So this is our region of integration. Okay. Now, when we change into polar coordinates, we always take say ray, and we consider this origin itself as a pole, and this OX as initial line. You know what are the polar coordinates system. This is initial line, not lines. Okay. And we think of a ray whose initial point, or a radius vector whose initial point is this pole in this region of integration, to determine the limits of the variable r. We know in the polar coordinate system the variables are r and theta. So to determine the limits of r, we take a ray like this. So here the minimum value of r is at this point. So r varies from 0 to this line. So we have to, sorry, not to this curve, that is the parabola. So you must first of all find the, say, polar equations of these two curves, y is equal to x square and y is equal to x. So let me consider here we have y is equal to x square, and another curve is, say, y is equal to x and y is equal to x. So what will happen if I put x equal to r cos theta and y is equal to r sin theta? I will get r sin theta. I want to change this curve, Cartesian curve, into polar coordinate system. So r cos theta square. So 1 r will be cancelled and you get sine theta is equal to r into cos square theta. Simplifying this further, I can rewrite this as r is equal to sine theta upon cos theta into 1 upon cos theta. That is nothing but r is equal to sec theta. This is sec theta, and sine theta upon cos theta is tan theta. Here we write y is equal to r sine theta and x is equal to r cos theta. So if you simplify, you get tan theta is equal to 1. R we can cancel, and sine theta upon cos theta is 1. So that gives me the equation of y equal to x, polar equation of y equal to x as theta is equal to pi by 4. And the polar equation of y is equal to x square, the parabola, is r is equal to sec theta into tan theta. Okay, so the required integral I can write as the double integral of it is not over r. Let me rewrite. So this double integral x equal to 0 to 1 and y is equal to x square to x of x square plus y square raised to minus 1 by 2 dx into dy, you can replace by writing what is x square plus y square. X square plus y square is r square, because we always take x equal to r cos theta and y is equal to r sin theta. Okay, I have not mentioned here. So we take, actually I should write here, take x equal to r cos theta and y is equal to r sin theta, and that gives us x square plus y square is equal to r square. So I can substitute x square plus y square is equal to r square in this, and just let me write as the same region as it is, r square raised to minus 1 by 2, and dx into dy is replaced by r into dr d theta by our transformation formula. Okay, and how does this r and theta changes? R changes from this point, r is equal to 0 to r is equal to this line, that this curve, that is sec theta into tan theta. And how does theta change? The minimum value of theta is at this point, which is on this line, that is theta is equal to 0, and the maximum value of the angle, that you can go in this direction. If we take all these different rays in this region of integration, you can see the maximum value of theta is obtained on this pink line, whose equation is theta is equal to pi by 4. Okay, so theta varies from 0 to pi by 4 and r varies from 0 to sec theta into tan theta. So I can write this integral as this is equal to integral, say theta is equal to 0 to pi by 4. I want to integrate with respect to r first. So integral r is equal to 0 to r is equal to sec theta into tan theta, and this becomes r raised to minus 1 into r into dr. Sorry, it is first with respect to, say, r. So I am writing theta dr. So integrating with respect to r first. So this is equal to theta is equal to 0 to pi by 4 into integral r equal to 0 to sec theta tan theta, and this r is to minus 1 into r is 1 dr, and then it is to be integrated with respect to theta. Okay, so simplifying further, what we get is theta is equal to 0 to pi by 4, and then integral of 1 is theta and r equal to 0 to r equal to, sorry, it is not theta because we are integrating with respect to r. So integral of 1 with respect to r is simply r. And the limits of integration is 0 and sec theta into tan theta. And then this is to be integrated with respect to theta finally. So if you put the values of limits of integration, what you will get is simply sec theta into tan theta and minus 0. So only this much. This is with respect to theta. And what is the integral of sec theta into tan theta? I no need to write this also. I can drop this brackets. So just simply integral of sec theta into tan theta, because if you put r equal to sec theta tan theta and r equal to 0, what you will get is only sec theta into tan theta d theta, which is a very simple integral. It's a derivative of sec theta is sec into tan, so integral of sec into tan is sec theta, and theta equal to 0 to pi by 4. Putting the values of limits of integration, we get sec pi by 4 minus sec 0. What is sec pi by 4? It is root 2, because cos pi by 4 is 1 by root 2. So sec pi by 4 is root 2, sec 0 is 1. So final answer is root 2 minus 1. So this is our required integral. Let me take some other interesting problem. A second example. Let us take some difficult one. Evaluate the double integral of the function 1 minus x square minus y square upon 1 plus x square plus y square dx dy over the region R, where the region R is given by all those points in R2, where x is greater than or equal to 0, y is greater than or equal to 0, and x square plus y square is less than or equal to 1. Okay. The region of integration is very simple. X greater than 0 and y greater than 0 means we are in the first quadrant, and x square plus y square is equal to 1 is the equation of unit circle, but we have to take all the points satisfying the condition x square plus y square less than or equal to 1. So this will be the set of all points inside the unit circle lying in the first quadrant. Okay, so it is very simple. So first of all, we just write down the region of integration. Let me the region R is bounded by x equal to 0, y equal to 0, and area of the unit circle x square plus y square is equal to 1 in the first quadrant. Okay, so it is easy to draw the region of integration here. So let me draw that first. So this is x-axis, and this is y-axis. And let us take a circle, unit circle, in this let me keep it over here. Fine. So region of integration is, this is x square plus y square is equal to 1. This is origin. Okay, so this is radius 1, and the region of integration is the this area in the first quadrant. Okay, so this is the origin of integration. As you can see that the function is very complicated, but one can understand that it contains the expression x square plus y square at these two places. I can take -1 common here and write 1 minus x square plus y square, and this is 1 plus x square plus y square. So it is better to change this into polar coordinates. Let me write. So changing into polar coordinates, changing the given integral, the given double integral into polar coordinates, to polar coordinates by taking x is equal to r cos theta, x is equal to r cos theta and y is equal to r sin theta, and we know that we replace dx dy by r into dr d theta. At the same time, we must also say we must change the curves which are the boundaries of the region of integration. This is the origin of integration, and it is bounded by this y equal to 0, that is x-axis, the y-axis, that is x equal to 0, and this circle x square plus y square is equal to 1. Okay. And now I'm taking the polar coordinate system here. So I'm taking this point origin as pole and x as initial line, the x-axis as initial line. To write down the limits of integration in the polar coordinates, we take an arbitrary ray or a radius vector in the region of integration. So this is my ray, and we have to identify the starting and the ending curve of this ray. So we are interested in integrating with respect to r. You can see clearly for any position of this ray, r varies from 0 to this circle. So what is the equation of this circle in terms of polar coordinates? We know that x square plus y square is equal to 1 means r square is equal to 1. So we have the equation of the circle is r is equal to plus or minus 1. But I will take r is equal to plus 1 here in this positive direction. So I am taking r is equal to 1. This is r equal to 0. So r varies from 0 to 1. And when you take all possibility, the angle theta varies from this point to this point. So theta varies from 0 to theta is equal to this. So theta is equal to 0 to theta is equal to pi by 2. Okay. So I can write down the required integral as, therefore, the double integral over the given region R of square root of 1 minus x square minus y square upon 1 plus x square plus y square dx dy is equal to double integral. So theta varies from 0 to pi by 2 and r varies from 0 to 1. Okay, and this function becomes square root of 1 minus r square, because x square plus y square is equal to r square, we know the relation x square plus y square is equal to r square. Relation between the polar and Cartesian coordinates upon 1 plus r square into r dr d theta. Okay. Or d theta dr rather, I should write in that order. This is equal to r, okay, this is equal to r into d theta into dr. Okay. Now, just I want to use one very interesting result which I will just mention. If we have double integral, okay, of function of two variables x and y, and all the limits are constant, say a to b, c to d, then and if you can express this f of x comma y as a product of two functions where both are independent of say, suppose this is the limit of x, this is the limit of y. Let me write like this. So if f of x comma y can be expressed as g of x into h of y, where the function g does not contain the variable y and the function h does not contain the variable x. If you can express fxy as the product of two functions where one function does not contain the parameter of the other function, and if all the limits are constant, then this can be evaluated by writing directly x is equal to a to b and simply g of x dx into integral y is equal to c to d, say h of y into dy. So here we have a similar situation. Here all the limits of r and theta are constants, and this r, this part is a function of r which does not contain any theta. So I can write this above integral. So the above integral, therefore we can write the above integral as integral theta is equal to 0 to pi by 4 1 into d theta multiplied by integral r is equal to 0 to 1 and square root of 1 minus r square upon 1 plus r square into r into dr. So we can express this as the product of these two integrals, because both the functions, this is a function of r and this is a function of theta, they are not containing each other and all limits are constants. Okay, so first part is very simple. Integral of this is theta and it is 0 to say pi by 2. It is not pi by 4, it is pi by 2. Yes. In our region of integration, here theta varies from 0 to pi by 2. Yes, here theta varies from 0 to pi by 2. Here also you can see 0 to pi by 2. And r varies from 0 to 1. But the second integral is a little bit complicated. Let us see how to solve that. Let me multiply and divide this this function inside the square root by 1 minus r square. So what I am going to do is I am multiplying and dividing by 1 minus r square. This r is also there into dr. Okay. So this is equal to this integral is very simple. Its value is pi by 2. I am writing directly. And this becomes r is equal to 0 to 1. 1 minus r square, 1 minus r square is simply 1 minus r square into r upon square root of 1 minus r raised to 4 into dr. This is a plus b, a minus b. So it is a square minus b square. Now let us integrate this. I think this can be done easily. Yeah. So this is equal to pi by 2 integral r is equal to 0 to 1. Okay. Let us multiply this r and we get r minus r cube. And I'm separating the denominator, so I can write this as 1 minus r raised to 4 dr. I'm writing directly integral r is equal to 0 to 1 r cube upon square root of 1 minus r raised to 4 dr. So what I have done is I have multiplied this r with this, expanding this and then separating the denominator. So a upon a minus b upon c is a upon c minus b upon c. It remains to find the value of these two integrals. For the first part, let us take a substitution. If I take, say, r square is equal to something, then derivative of r square is 2r. So I can adjust this term. And this is very simple. It is something like, say, derivative of r raised to 4 is 4r cube. And so r cube is in the numerator. It is something like f dash x upon root fx. Okay. So just let me take the substitution. Taking only for this, taking r raised to 4 is equal to t, we get dt is equal to, sorry, it is not r raised to 4 is equal to t. I want to take only r square is equal to t. Taking r square is equal to t, I will get dt is equal to 2r dr. Also, the limits will change now. When r is equal to 0, we have t is equal to 0. And when r is equal to 1, we have t is equal to 1. These limits of integration must be changed in the definite integral whenever you take any substitution. So this I can write as, this is equal to pi by 2 into integral t equal to 0 to 1, and this r into dr I can replace by, say, 1 by 2 times dt upon square root of 1 minus t square. Fine. And minus derivative of 1 minus r raised to 4 for this second integral is minus 4r cube. So let me write this way, plus, say, 1 by 4. I am multiplying and dividing by 4 for the second integral, 0 to 1. It is 4r cube with minus sign. I have taken this minus sign inside and writing like this, 1 minus r raised to 4 dr. Okay. So what is the next step? Very simple. This is equal to pi by 2 into integral of 1 upon square root of 1 minus t square is sine inverse t. This 1 upon 2 as it is. And integral of 1 upon square root of 1 minus t square is sine inverse t, and t equal to 0 to 1. Plus 1 by 4. This is something like f dash x upon root fx. So its integral is 2 root fx. So 2 root 1 minus r raised to 4, and r is equal to 0 to 1. So you will get this. Okay. So this I can write as, remember I have used this formula, integral f dash x upon fx. Let me write just for your reference, because integral of f dash x upon root fx is equal to 2 times root fx. So you know this formula, the standard formula. So this gives us, this is equal to pi by 2. Sine inverse 1 is again pi by 2. So it is sine inverse 1 minus sine inverse 0. And here 1 by 4 times when you put r equal to 1 first, I will get 2 into 0, and when you put r is equal to 0, you will get 2 into square root of 1, that is 1. Okay, so what is the final answer? This is equal to pi by 2 into 1 by 2. Sine inverse 1 is pi by 2, sine inverse 0 is 0, and plus this is what? It is not plus, it is minus 1 by 2. This is equal to minus 1 by 2. So simplifying further, what will be the final answer is very simple. It is pi square by 8 minus pi by 4. Okay, so this is the answer for this problem. So this way you can solve the problems of say transforming from Cartesian to polar coordinates. So we have done these two interesting problems. Now you can practice some more examples of this type. Okay, so in the next lecture I am going to discuss how to change the Cartesian coordinates into say spherical or cylindrical coordinates. So we'll take different lectures for transforming into different coordinate systems. So till then, goodbye.